All right. My name is Samuel Schmidgall, and today our lecture is going to be learning like the brain. So we're going to kind of take the neuromorphic paradigm that you guys have been looking at so far, and I'm sure the majority of like the cases you're looking at is with fixed weights, and we'll get into what that means later. But we're going to look more closely at using plastic weights and how all this relates to what's happening in AI right now. So the first part of the lecture, we're just going to go through some basic neuroscience, and I've made it very brief and very dense. So don't feel bad if you don't absorb it all. It's just we're just trying to get a feel for what's happening in the brain. Okay, part one, neuronal processes. So now we're just going to go through a short simplified summary of neural computation. So we're starting with zero knowledge. The brain is composed of neurons, which are connected with other neurons in network-like structures. And there's actually a lot of other neurons, or there's a lot of other types of cells in the brain. There's, astrocytes and glial cells, but the majority of, I guess, the interesting things that are happening are coming from these neurons. Outgoing connections are called axons between neurons, and incoming connections are called dendrites. And binary signals are produced by the neuron. These signals are transmitted down the axon, and the axon transmits it to the presynapse. You can kind of see in that picture over here, where it's highlighted, you can see it's not actually a direct connection between two neurons. There's these little knobs, and those are called synapses. And there's a presynapse and a postsynapse. And these are actually really important parts of the neuron, which we're going to talk a lot about. So yeah. The neuron acts a lot like a capacitor, accumulating voltage in the soma. And when the amount of voltage reaches a certain critical threshold, it spikes. I'm sure you guys have been over this a bunch. The spike travels down the axon to the synapse, where it connects to neighboring neurons. And this one's a bit interesting. Synapses communicate via chemicals instead of through electricity. So when you see the action potential traveling from the neuron all the way down, it doesn't actually go all the way to the next neuron. It reaches the synapse releases a bunch of chemicals, and then those chemicals reach another synapse, and then those generate an action potential at the next neuron. So it's kind of has this like intermediate step that's going on, and all of that is happening chemically. And that's because, for one, it's really energy efficient. Producing these electrical signals is very expensive. It creates this unidirectionality. So you can't go back, but you can go forward, right? So the receiving synapse can't like produce chemicals that push back. It just creates this unidirectional signal, which is pretty important computationally speaking. And it has some other interesting properties which are very important for learning, which wouldn't necessarily be possible with an electrical synapse. So we'll talk about this later on. Once again, it acts a lot like a capacitor. Ion channels allow the passage of ions across the cell membrane, and these ion channels open as charge is put on the neuron. And so kind of when the neuron passes the signal down, then it kind of opens these ion channels and a bunch of ions flood into the neuron. There's a lot of different types of ion channels, but the most common in the brain are voltage gated, which means when a voltage is on the neuron, the ion channels kind of open, and that's when the neurons flood, or the ions flood in. And there's also another one, which we're going to talk about in the next slide, which is in the absence of stimuli. There's actually, when there's no dendritic input, the membrane potential is still continually changing. And you might be wondering, why is it changing if it's supposed to be acting like a capacitor? That's because the neuron passively transfers ions even when there's no activity, which draws the membrane potential back to the neuron's resting potential. So basically, in the absence of any stimuli, the voltage inside the neuron is just going to go back to zero over time. And that's because there's these sodium potassium pumps where they trade 2 positive potassium ions for 3 sodium ions that are on the inside. So basically you're pumping out 3, like the number 3 on the inside for the number 2 on the outside. And basically this creates a net negative trade. And so slowly you're getting more and more negative until you reach a certain value. And then that's kind of when you stop making these trades. Okay. But, you know, critically, this takes time, right? It doesn't just instantly go to zero in the absence of activity. You're slowly decaying your activity over time. And I'm sure you guys looked at the leaky integrating fire. Yeah, so that's kind of what's happening in the leaky integrating fire. That's the leak component. That's just the cellular mechanism of that. Okay, now that we know how an action potential is produced, action potentials, once again, are not usually carried all the way down the axon from the pre-neuron to the connecting post-neuron. In chemical synapses, which there are other types of synapses, but we're going to pretend they don't exist for this lecture. When an action potential travels down the pre-neuron axon to the presynapse, the presynapse releases chemicals which induce a graded electrical activity at the connected postsynapse. And so what I mean by a graded electrical activity is basically these synapses have a particular size, right? So they can be really small or they can be really big. And so if they're really big, then they're going to release a ton of chemicals, right? And that's going to induce a much larger amount of activity in the postsynaptic neuron than if you just had a small amount of chemicals, right? And so the graded kind of means attributed to all of these synapses, there's a magnitude that the effect a spike has on the post neuron. So like, even though the signals are binary, 1 or 0, the synapse produces this kind of continuous range of values. So you could think of it between 0 and 1. So yes, we are producing a 0 and a 1, but we're actually also scaling that based on the size of the synapse and the amount of chemicals it releases. So functionally, it's not really binary in this sense. Yeah, and just the chemicals that are being released are called neurotransmitters. It's actually a bit more complicated than that. Synaptic transmissions are influenced by external neurotransmitters that are not necessarily local at the synapse. So, right, you don't necessarily need an action potential to produce those chemicals that create activity at the synapse, but there are also neurotransmitters that are broadly diffused, like all across the brain, from activity that may not even be close to where it's affecting, right? And these neurotransmitters can be based on really a lot of different things. So for example, like just a intuitive example, let's say, I don't know, you're walking down the street in a very weird way that you've never walked before. Like, I don't know, you just are walking funny, and then somebody jumps out and surprises you. A very random occurrence, right? Your brain, even though all the behaviors that produce that motion are not necessarily connected to your eyes and ears, which are the things that perceived, you know, somebody jumping out and scaring you, they somehow connect, right? So you're going to associate now the way you were walking with this very surprising event. And that's because things that are happening very far in the brain can basically affect behaviors that are happening somewhere else by diffusing these neurotransmitters to different areas of the brain. So, you know, these can really happen for a bunch of things. Let's just say fear. Let's just say you take a bunch of actions and something really great happens, and you know, some reward chemicals are signaling through your brain, or surprise, like we just mentioned, as well as just general regulatory processes. And typically, synaptic changes are consolidated in the presence of these external transmitters. This might be confusing now. We're gonna talk about this later, but so the synapses are very dynamic, and they only change in the presence of external transmitters. They don't change necessarily just by themselves through, the classic STDP paradigm I'm sure you guys looked at. They don't just change in this unsupervised way. They also have a lot of supervision that's happening all throughout the brain. And this is kind of the biological equivalence of all of that. Okay, it's actually a lot more complicated. Each neuron has a cell type, which is only responsive to certain types of neurotransmitters. Also, neurons themselves are the things producing the neurotransmitters that are diffused across the brain. And thus the behavior of neurotransmitters that are released are kind of affected by the same neurons that receive them. So it kind of gets really complicated and messy and confusing. I'm just mentioning all of this just to show you how complicated it is and how little we understand currently, even from the neuroscience side. And then, here's some very confusing images that are supposed to confuse you, because I don't understand them. I don't even close to understand these. But there's a lot of things happening here, and we're taking a very abstract picture of all of this that has been refined over the years. Okay, let's take a look at some abstractions. But first, does anybody have any questions about any of that, or want to go back to any slides? No? Anyone in the Zoom? Okay.
No.
So let's take a look at this idea of a phenomenological model. As we saw, everything in the brain is super complicated, and there's just so many things happening at so many different scales. You have the genetic scale, you have the chemical scale, you have all these proteins and all these different things interacting together. And as all of us here are in some way engineers, we do care about that, but not really in the same way that neuroscientists care about that. We just really want to understand, how do we take the underlying dynamics of what makes the brain without all the messy details? Because we want to harness the capability of the intelligence of the brain, but we don't really want to deal with all the, biological details. And so this is kind of what phenomenological models allow us to do. They attempt to capture the fundamental essence of a neural process while abstracting out all the messy biological and chemical details. And so we want to move toward higher abstraction that still captures as much of the biological process as is necessary to, still benefit from brain-like computation. So on the right, you have something at the top, you have something very scary, and nobody likes that. And at the bottom, you have something that's kind of nice and simple and understandable, and we do like that. So a particularly interesting model, which we have probably looked at before, is the leaky integrated fire. What the leaky integrated fire neuron does is it receives spiking information from neurons that connect to it. And this information is integrated into the neuron's membrane potential. And this membrane potential has a leak component, which basically, it stores all the information, but this information slowly goes back to zero over time. It's exactly what we saw earlier with the ion channels, which were, accumulating all this information and then over time decaying that. And so this kind of is a really simple model and a really simple way of, capturing the essence of this process. When you connect all these together in complex and interesting ways, we get a spiking neural network. But something that's largely ignored is what happened to the synapse here, right? We took this super complex and dynamic synapse. We learned about, a little bit about how complicated it is and all the things that are happening in it. And we just reduced it to a simple linear coefficient, which we call the weight, right? You have a neuron and it's emitting a spike to all of its connected neurons. And basically this spike, which is 1 or 0, is being scaled by some W sub ij, which is just the weight from neuron I going to neuron J. And really all that's happening is you're just multiplying by, a scalar value. And that's kind of the majority of what's happening in both the world of AI and the world of neuromorphic computing. And it's like all phenomenological models, a massive oversimplification. So now we're going to take a look at AI, like just a little bit of the history of AI and what's been happening in the world of AI. And then we're going to come back to all of these models of leaking a grain fire, synaptic plasticity. And then we're going to talk about how all of them can, come together and produce an adaptive sort of intelligence that kind of emulates how the brain works. Okay, so we're going to take a short journey through the history of AI. One, because it's exciting, and two, because it's very well integrated into a lot of what's happening right now with neuromorphic engineering. Like, why do people believe in neuromorphic computing? Why does this field exist? How does it relate to the history of AI? So AI was born in the 1950s, which is basically the exact same time that the first computers were being created. The field of AI was founded to understand how to develop human-like intelligence into computers, basically. And naturally, the first researchers trying to understand this were developing models of the brain, the origin of the only intelligence that we know of today. So long story short, there were way too many hurdles getting in the way of getting these things to work back then. And many people in AI over time had begun criticizing brain-inspired approaches to developing intelligence in favor of logical and mathematical-based approaches to intelligence. A lot of people back then believed that, if you wanted to create a really powerful robot or a really powerful image classifier, you could just design all these logical if-else statements and just create the ultimate machine that can solve every problem. So it sounds absolutely crazy today, because we know that that's absolutely a terrible idea. But genuinely, there was two big sides of AI. There was the logic approach and there was the brain-inspired approach. And we're going to take a look at how it went for the logic approach people. Okay, so AI has kind of a pretty rough history, unlike a lot of other fields. They call them the AI winters. AI kind of has a series of, a lot of hype and a lot of funding and a lot of attention, from the media and from everything. And then it's just followed by, a bunch of winters, which basically nobody funds AI research, and basically it kind of dies for a while. So the first wave of excitement came in AI with the development of the first neural networks and perceptrons, which are basically a very simplified version of an integrate and fire neuron, just minus any integration. However, there was a researcher, his name was Marvin Minsky. He wrote a very influential book discussing how neural networks are too limited to solve hard problems. And this presented any funding for neural network-based ideas for several decades, actually. So once this book was written and he was just saying, basically talking bad about neural networks, nobody funded it for 20, 30 years. The second phase was there was this renewed AI excitement about these ideas of expert systems. Have any of you guys heard of expert systems? Okay, there's a good reason you've never heard of them, but expert systems, I guess back in the 1980s, had the same amount of excitement around them as neural networks do today. Perhaps not the same quantity, but it's, people were talking about it in the news, all these crazy expert system ideas were being tossed around. And then they just realized they were terrible. And, it was kind of what an expert system was they were basically would take human experts, and the human experts would try to dump all of their knowledge into a database. It is ridiculous, but they would dump all their ideas into a database, and they would try to design robots that use that information to solve problems. It's absolutely crazy. But funding accelerated, and then people realized there were so many limitations with this type of problem solving. And then nobody funded AI for like any AI research really for like 15, 20 years. Or let me see the timeline. It looks like 10 years. And currently we're in an AI summer. There's been a slow and steady progress toward bigger and better AI systems since the mid 1990s. 1990s is kind of when the convolutional neural network was invented. It's kind of when the MNIST data set was created. And people were starting to realize that neural networks actually aren't that bad as they originally thought. And just the past 25 years, we've made a lot of progress. Also, backpropagation was invented, which was probably the biggest contributor. But then also just better computers were around, so we could solve bigger and better problems. And that's kind of where we are today. But there is a lot of speculation. There's been a rise and a fall and a rise and a fall and a rise. And every single time there's this rise, people are so excited about AI and like so optimistic about what it can solve. And then they just realize it can't solve the problems that they thought it would solve. So where are we headed? We've seen so much tremendous progress in the past 2 decades, but there's a lot of uncertainty about where we're headed in the future. Are we reaching a limit? Are we deviating off the right path? We really don't know. But there is a pattern in the cycle of brain-like machines. Oh, can you guys not see well? Oh, okay. There's been a pattern in all these rises and falls, and it's just that the original ideas put forth at the beginning of the history of AI were to build machines that emulate the brain. And after all this time, the most powerful models of AI still resemble the brain with learning algorithms that loosely resemble how learning occurs in the brain. So basically, after all this investment, all this time, all this research, we're kind of still where we started, which is following ideas in the brain. And neuromorphic computing is kind of built off the belief, and I use belief very intentionally, that following the brain is the right path toward developing intelligent machines. Okay, so I'm sure you guys know what a neural network is, but I kind of have this slide because I want you to conceptualize it in a unique way that I've heard before that I really like. One of the conceptualizations I've heard of what a neural network is a giant computer program. And basically, the code for the computer program is the weights. And when you change the code, the computer program changes its function. So you give a neural network an input and you get a magic output. And basically the objective of all deep learning in AI is just to get something, the program to output something useful, Yeah, and so artificial neural networks are composed of neurons and synapses, and the neurons are represented as a nonlinearity, typically some mathematical function like a tanh or a sine or a ReLU. And synapses are just these linear coefficients that we talked about earlier. Neurons take an input and, you shove it through the network, you get an output. It's pretty simple. It's just some matrix multiplication. And this is kind of the math behind it. Are you guys like super comfortable with this? Like you don't even want to look at this? Or you want to maybe talk about it a little bit? What? Both? Okay. I don't want you guys to be bored if you're super comfortable with this. Okay. So we'll just take a look at this. So this is a single neuron, right? And we can think of the X1, the X2, all the way to the Xn as just some set of neurons that are connected to this neuron. And these W1, W2, Wn are all the weights of the connections to this neuron. And basically all the neuron does is it takes all the activity at the neurons from that are connecting to it, and that activity is multiplied by the weights, and then all of that activity is summed, right? And then you apply some function to it. So, you apply a tan H to that, and then you propagate that information. It's really simple. And in the vast majority of all AI systems today, there's no concept of memory, right? You shove all this input through, and once you get an output, the neural network has no conception of time, right? You shove an input through, it doesn't remember that input at the next time step. It just it's a blank slate. It completely forgets everything at the next time step. And this is actually a little bit problematic, and we're going to look at that in a minute. Spiking neural networks, you guys are very familiar with these. I just wanted to mention that they are still artificial neural networks. They're still the exact same thing. The only difference is instead of using this tan H or this ReLU, we're just using a spiking function. So the only difference is we're getting a 1 or a 0 as the output. Otherwise, everything's the exact same. It just more closely resembles biology. And when we modify the weights of these networks, we see all these functional changes occurring at the output. Okay. So this image on the right here was actually generated by an AI. Do you guys know which one that is? DALL-E 2? Okay, well, I actually have access to this. You can so basically how this AI works is you can input some prompt for an image. So I don't know, this one's probably two mad scientist bears doing an experiment, and it actually generates this image from scratch, which is pretty impressive in my opinion. I wanted to show that because I wanted to show how training neural networks with backpropagation is extremely powerful. You can do a lot with it today that we didn't even think was possible just 2 years ago. And basically how it works is you accumulate experience, right? So experience we're going to define as you have a bunch of sensory input, you shove that sensory input through the network and you get output. And the experience is the relationship between input and output and consequences in the environment. So we can talk about consequences as you have a loss function. The consequences of producing a bad output with a loss function is a high loss. The consequences of producing a good output is a low loss. So we're kind of abstracting the concept of experience a little bit here. The second thing you do is you calculate a weight change based on pre and postsynaptic activity, as well as an error signal. And this kind of goes more into depth with how backpropagation works. And we're going to take a look at backprop in a second. And then the third step is you just propagate errors back through the network. This should seem a little bit familiar. I kind of worded it in a way that relates it back to how the synapse works. And that's because backpropagation and synaptic plasticity are actually pretty deeply related. Okay. So backpropagation is an algorithm for obtaining the gradient of the weights in a deep multi-layered neural network with respect to a loss function. And the loss function provides, like I just mentioned, an error between the network's behavior and the behavior you want it to produce. So if you have your classic MNIST data set, you shove the image through and it tells you, a 1 is a 7. You're not going to be that happy about it. You're going to give it a massive error. And then the network's going to try to fix its weights, change its weights such that it's more likely to see a 1 and output a 1 label. And basically what you do is you take the gradient of the weights. So we go back to calculus. You take the gradient of each of the synaptic weights with respect to a loss function. And that's how you can determine how to change the weights such that you get better performance on that loss function. And understanding backprop is pretty difficult. So we're not going to actually go into the mathematics of that, but basically you just propagate the errors backward through the network. Yeah, that's why it's called backprop. Yeah, so at the end of the day, backpropagation is an algorithm that works just because people tried it and it worked well. There's not like this deep theory surrounding the success of deep neural networks with backpropagation. People just kind of believed it would work well, and they were right, you know? There's no like just really rich, like I don't know if you've studied support vector machines or like classical statistical models, but like we know for a fact that those are the best models in a lot of circumstances. We don't know anything about backprop, right? We just know that when we use it, it works. And that's kind of an interesting thing, because, you know, it's just odd, right? We don't have any we don't have any certainty that it is the best. We just kind of tried it and it worked. So it's pretty conceptually simple to understand. You know, you're just shoving the error backward and then changing the weights. But it's very difficult to actually implement in software, which is why a lot of us are using stuff like TensorFlow or PyTorch, because it just makes the implementation very easy. But if you take anything away, just remember backprop is taking the derivative of the weights with respect to a loss function. And that's how it's working. Okay, now let's look at a case study. Training neural networks to control robots. This is one of my favorite areas of AI. This is actually what I work on. And we're not going to go too in depth on how it works. It uses something called reinforcement learning. And reinforcement learning could be a 3-hour lecture just by itself. It's very complicated, but do I talk about it? Yeah, okay. We'll just get the essence of it right here. So basically how it works is you collect a bunch of experience from a simulator. Let's say you have like this robot arm, and this robot arm, you know, you start off with some neural network that's controlling this robot arm. And you get a bunch of sensory information from the robot arm. You put it through the network, and then for the robot arm, you're producing torques. You're just producing like motor behavior. And then the arm does that motor behavior controlled by the neural network, and you tell it whether that motor behavior was good or bad. And so, you know, it starts off going crazy with its arm, and over time you improve behavior using backpropagation, making good behaviors more likely and bad behaviors less likely. Eventually the robot improves a lot and it looks good to us in simulation. And so we try to deploy the robot in the real world. And one thing I want to look at here is below that moving robot picture, you see how there's these up, down, up, down, up, down, and then it's win, lose, lose, win. So basically, if you're playing like a game of Pong or something, you have to, if you want to update the weights, you have to play like 20 games, right? And then you average your performance across those 20 games, and that's how you make a change to your behavior, right? Do you see any problems with that, perhaps? Let's consider the robot case, right? Anyone wanna guess, or what do you say? Yeah, okay, so we'll go back to this slide. So if you see right here, you see this bar done. Yeah, so if you see right there, there's kind of a bunch of ups and downs and ups and downs. And basically what that's trying to show is to do a single reinforcement learning update, you need to play a bunch of Pong games, like entire Pong games. And then once you've played a bunch of those, then you update the weights. The weights aren't being updated during the time it's playing, right? It begins playing the game with a fixed set of behaviors, and then it plays a ton of games, and then it learns, right? And so there are problems with this. And does that make sense, by the way? Okay. So what if we train our robot to walk in simulation, just up and down stairs, right? And on flat terrain, you know, it's just doing things you want a robot to do. But what if you now deploy this robot in the real world and it encounters something it's never encountered before? What if it encounters a wall or a car or a person or like water, right? What if it runs headfirst into a wall and just like, you know, slams its head into a wall? The problem is it's not going to be less likely to do that in the future, because once you've trained it in simulation, you know, you're collecting all these lifetimes of the robot and then you're updating the weights. But anything that it encounters during its lifetime, it doesn't learn how to adjust to that behavior, right? So maybe in the simulator, it slams its head into a wall like 50 times and it doesn't learn anything, but then you do a gradient update and it figures out not to slam its head into a wall. But once you deploy it on the real robot, it can't learn anything new. And if you've ever owned robotic hardware, you know it's expensive, and if it slams its head into a wall 50 times, you will be in a lot of trouble and owe a lot of money. So we don't want it to do that. We want it to maximum slam its head into the wall like 2 times. So that's our goal here. Oh.
Causal system is very different. We talk in terms of causal system. If we what? Causality of a system. Yeah. So we can't define causal system that makes like the causal systems are not harming things.
So causal systems could relate, for example, slamming your head in the wall to a bad behavior. But the problem with neural networks is there's not a lot of causality that's happening. You know, you have this big machine and you kind of don't really know what's happening on the inside of it. And slamming your head into a wall is not a very easy behavior to define when you're a robot, right? Yeah. A causal system. So a causal system is a type of AI system where it reasons about outcomes based on what it thinks caused them, right? That you'd say that's a yeah. Okay. Can you guys hear in the they're talking about why can't we just have a causal system? And a causal system is basically, you know, when you relate the causation of an outcome to something explicit. And like for in this case, slamming its head into a wall to something bad. And we were saying because it's difficult to relate causation in a neural network that's doing some behavior like this. Right. Does that make sense? Okay. Yeah, I mean, if we looked at, we can look at the equations for how robots are trained to, you know, produce good behaviors, but it's like shockingly simple and it's very surprising that it works. It's actually very interesting. So we can definitely look at that if you guys want later. Okay. So yeah, these robots can't adapt. In the traditional machine learning paradigm, once these programs are trained and deployed on a physical robot, they can't learn from new experience anymore. And you might be thinking, why can't we just do backprop on the actual robot? And there's a lot of problems with that, which are fundamental to the backpropagation algorithm. So when you do backpropagation, you may have heard of something called catastrophic forgetting. And basically, when you continually use backprop, anything you learned in the past is going to be wiped. It only cares about what you're learning right now. And so people that are using these types of methods on reinforcement learning applications for robotics don't really have a solution. They're training these things in simulation and they're not really working in reality. There's no way to adapt to reality from a simulator.
Create another layer of arguments, the set of neurons,
Mhm.
it can store basically the argument goes from the previous weight and it updates to the separate neuron.
Are you saying a method for overcoming catastrophic forgetting?
If we create another set of memory.
Yeah, so some people have done something like that. So there are methods for mitigating or like reducing catastrophic forgetting. And that's actually very related to one type of approach where basically you just add new parts of the network and you preserve the old parts and you just update those.
Just like the fusion.
Yeah, so some people have done that. And that could work. I've never personally read somebody do that, so perhaps that'd be something good to explore. Yeah, so this is actually one of the most significant mysteries that's happening in applying reinforcement learning to robotic systems. So, right, you have this simulated robot on the left, and you have this real robot on the right. But all of your training happens on that simulated robot with simulated physics. It's not like it's not the real world. And so you can imagine it doesn't match with real physics and with the real robot.
In this simulative environment is also similar to the real when they are trying to make the simulation.
What'd you say?
The simulation environment is also they try to make that as real as possible.
Yeah, they want to make it as real as possible, but if you just use an out-of-the-box simulator, it's not going to work. You're going to train a bunch on the simulator, and then you go to the physical robot, and they just don't match quite enough, and it fails.
I think if we talk in terms of robotic perspective, so where we don't consider a lot of parameters like stability and other control system parameters. Like more what we have to think in towards robotics. Then our simulations are more towards kind of AI side than of integrating it towards into the whole system.
What are you saying?
So whatever the simulations that we have to do, it was more like, is it going to be best from the AI perspective? Like, if I create that system that so it's going to be like, is it going to understand that something is going to hit or not? Is it what that thing is more, even more priorities than the stability of a system or something like that?
Physics environment.
What are they? I mean, like I think it's more of towards AI perspective than considering the robots, because I think that robotics is what like missing in the the control system part of the robots is like where it's get a little bit of less priority than the
I think that people are designing these with the robotic application in mind.
there is a trade-off. That is what I was thinking.
Yeah, exactly. There's a trade-off, and that has a lot to do with just kind of who's designing the simulator, how they designed it, and there's obviously a computational complexity added to making it physically realistic. And if it's too complicated, you can't actually solve real problems on it.
Because I personally worked on a few anti-learning. So when I was learning some anti-learning, like the environment in the software, and it was way different when I was doing that in an
Okay. Yeah.
I think this is the same thing that is happening.
I think a lot of people are dealing with transferring from simulation to reality. So I don't know if you guys have taken an AI class and or dealt with convolutional neural networks, but there's a lot of I guess problems with them. So there's this really famous paper that talks about this super impressive, deep neural network that can classify all sorts of images. Then you change one pixel and, a car turns into a frog. You can't even see the pixel as a human. But now the AI system, because you change one pixel, thinks it's a frog. And that's a classic example of overfitting to the data. And so what a lot of people are speculating is we're overfitting to the data here. We're overfitting to the simulator, and it's not allowing us to generalize to the real world.
What is the adaptive?
Oh, I don't know. I just copied this off Google. Oh, yes. All these pictures I completely copied off Google and did not credit any of them. So, but anyways, yeah, they have a robot and it adapts. They add some adaptive component and now it can walk in reality. So, yeah, there might be something on its feet. Could be like some sensor, or maybe it adds friction, or maybe it's like,
Regular multiplexing of multiplexing of the signals that from the reflex sensor, and it's not getting support with that. That's what it is.
yeah, probably something like that. I don't know.
When it comes to designing from the system on a simulation to the actual, there will be always a trade-off that we have to consider these kind of stabilities are the one which, because in that simulation you take it as a default, and when you make it as a certain physical one, you have to take every parameter, like you have to consider how much power is going to that.
Yeah.
If if in all three legs there is some certain amount of power and the other leg is not getting that required power, it's going to be your unstable system.
Sure. Yeah, I mean, there's a lot of ways it could go wrong, especially with robots. I think a lot of AI applications are kind of protected from the real world. Robotics are not. So yeah. Anyways, there's the robot that has an adaptive capability that can walk, and there's one that does not, that can't. There could be a million reasons why it's not working. It could be the training, it could be the physics simulator, it could be something wrong with the actual robot. But at the end of the day, it can't learn from its experience in real world. And that's a big problem. And that's where learning like the brain comes in. We're going to take a look at the synapse again. It's kind of got this cool image here where you see the two neurons there, and they're kind of just in a very weird way, just like modifying their own structure, right? To try and, I don't know, do something. But yeah, so one thing we should talk about is that the synapse is far from stable, right? It's not like your brain creates, or your genetics and your experiences create your brain, and then it just sticks there like without changing. It's just constantly changing throughout your life. Probably from the start of this lecture to the end of this lecture, your brain is probably not very different, but in some ways it's different. And so it's just constantly adapting itself. That's where synaptic plasticity comes in. The brain miraculously learns everything purely based on genetics and experience, which is kind of subtle, but it's also kind of crazy, right? You're just taking an input from your eyes, you're taking an input from your ears, and you're producing outputs through your mouth or your arms and everything, and that creates your brain, which is pretty crazy. One of the most important processes which underlies learning is synaptic plasticity. And plasticity is just the ability of the brain to change and adapt to new information. And synaptic plasticity is changes that occur at the synapse based on experience. And it's synaptic plasticity is kind of, at least in the neuroscience literature, speculated to underlie most of our intelligence. right? Most of our ability to learn and adapt. There's also a lot of other things that are happening. If there's a neuroscientist in the Zoom, they would probably be annoyed at me, but for saying that. But at the end of the day, it does produce. It is contributed for the majority of our ability to learn. Okay, and there is a beautiful relationship between backpropagation and synaptic plasticity. In the case of backpropagation, we modified the synapse by collecting a ton of experience, calculating an error, and updating the weights based on the derivative. In synaptic plasticity, however, the weights are constantly changing as the network collects new experience, allowing the network to learn during its lifetime, which backpropagation doesn't allow us to do, but backpropagation is in a way emulating this process at discrete intervals, right? So it's like backpropagation is turning plasticity on sometimes and then turning plasticity off for like a longer period of time, right? And it's interesting because it's not what the brain does, but kind of a little bit. And we'll look at that a little bit later. Yeah, in 2 slides. And then we're going to talk a little bit more about that when we look at the paper. But yeah, anyways, if we introduce synaptic plasticity into artificial neural networks or spiking neural networks, we can produce adaptive behaviors in our neural networks. And for example, our robots can slam their heads into a wall and understand the consequences of that action, which they couldn't do before. Let's just real quick look at STDP. I kept it really simple because I assumed you guys already knew about this. But there's 2 primary ingredients. One is we have a history of the spike timings for pre and postsynaptic spikes. You can see that at the top there, we have X sub j of t, which is the trace of the presynaptic spike. And you can see the presynaptic spike firing, the blue things that are labeled pre, and it's creating that time history trace. And then you have the post, which is creating a post history trace. And basically these kind of aggregate together to create STDP. Did you guys go into depth with this? Do you understand these equations? No? Okay. Okay, I'll explain these then. I wish I could use the whiteboard, but I don't know how to get that on the Zoom. Let's see how many people are on the Zoom. Okay. So I will explain it without the whiteboard. Okay. So let's look at the equation on the left at the top. You have some variable x sub I, superscripted by L. We're just going to call this the trace of, I don't know, neuron I in layer L. So it's basically just think of a single neuron. Okay, it's just a neuron. There's a lot of fancy mathematical details happening here, but you just have a single neuron, and kind of like how the leaky integrate in fire was accumulating information and then leaking it, that's exactly what's happening here. Every time a spike occurs, you're accumulating information, however, not at the neuron, at the synapse. And kind of with a pretty rapid time constant, you're decaying that information. So you kind of see the alpha and then the X. So that's just the decay component. That's the leaky component, because the alpha is going to be less than 1. And on the right side of the equation, it's summing some quantity, which is the function, by a spike. And that's going to be just some amount of information that's being accumulated in the synapse. So basically, you're just aggregating this decaying trace of information at the synapse. And what happens is you do that for pre and postsynaptic neurons. And then in the presence of Okay, so there's two components of spike time independent plasticity. There's depression and there's potentiation. And potentiation is when you increase the synaptic weight. So, if you take, let's just say for backprop, if you take the derivative with respect to a loss function and increasing the weight produces a positive change, then you raise the weight. If you decrease it, if it would be better to decrease it, you decrease it, and that lowers the weight. And lowering it is depression, increasing is potentiation. And so what STDP does is it models the same thing, but without the derivative, without any external information. So just purely based on pre and postsynaptic information, you're updating the synaptic weight. So information here is the pre and postsynaptic spikes.
What's the S term is like?
What is the S? S sub I? Is that what you mean? Okay, yeah, the S sub I is a spike happening at neuron I. So you can imagine you have neuron I connected to neuron J, and neuron I produces a spike. It travels down the axon to the synapse, and the synapse kind of accumulates that information. So the synapse is X here, and the spike at neuron I is the S. Yeah, I should have mentioned that. S is the spike. And then let's look at the second equation there. So Wi sub j is the weight of neuron I connected to neuron J. And what's going to happen here is you're going to see you have some eta. That's that fancy Greek symbol right there. You're going to have eta positive going from I to J multiplied by X sub I multiplied by S sub J. Okay. And so when S sub J is the postsynaptic spike and X sub I is the presynaptic trace. And so when the postsynaptic neuron spikes and the presynaptic trace has a large value, then the synapse gets larger. When the presynaptic neuron fires and the postsynaptic trace is large, then it shrinks. And basically the intuition behind this is when you have a presynaptic neuron producing a spike in the postsynaptic neuron, they become more correlated. So it's basically the presynaptic neuron is causing the postsynaptic neuron to fire, and so their synapse increases. So you kind of strengthen that relationship. If the postsynaptic neuron is firing, but in the presynaptic neuron, X sub J, yeah, and the presynaptic neuron fires, and the postsynaptic neuron doesn't fire, you kind of decrease that relationship. So if it's kind of this correlation mechanism, and they kind of, without any guidance, kind of produce their own like strengthening and weakening. Yeah, I mean, there's not really an intuition behind it from a learning perspective, because basically how they arrived at this was they just looked at synapses and tried to model their behavior. They weren't trying to come up with some clever learning algorithm for AI. This was like neuroscientists looking at brain data, and this is what they saw. Oh, okay. And so there's one problem with plasticity models if we're trying to solve real problems, and that's that there's no signal that's attracting behavior. There's no signal that's attracting the neural network toward any particular behavior, right? Like you could have this spike time independent plasticity rule, but we want a robot to learn how to walk. We don't care about, this unsupervised, just growing and shrinking of synapses. And so that's kind of where neuromodulation comes in. Neuromodulation, if you remember, was those signals that were diffused all across the brain. And basically, if we're going to go back to the robot slamming its head in the wall, if the robot slams its head into the wall, it feels pain in its like nerve receptors. And basically whatever caused that, like that pain produces chemicals in the brain that try to make that behavior less likely because the brain doesn't want to feel pain. And so basically how we modify our synaptic plasticity rule is we only update the weights in the presence of a neuromodulatory signal. And so if we kind of equate this to backpropagation, like let's say we have some loss function. Let's say the network does really well on the loss function, like to the point where it gets 0 error. You don't want to update the network. You know, the change is going to be 0. But if there's a massive loss, you want to make massive changes. If there's only a little bit of loss, you just want to make a little bit of changes. And that's kind of what's going on here. So we're not going to just be constantly changing. We're going to be changing constantly, but in the presence of some signal that guides change, I guess. Any questions on that? Okay, I want to see where we are with time. Oh, it's only been an hour. It's kind of the end of my slides. Yeah, kind of the last thing I had, I thought that would be 2.5 hours. Okay. Do you guys want to look at a paper for, oh yeah. Adaptive synaptic plasticity. What do you mean by that? Yeah. Okay. I've never heard of that. We could, yeah, we could look into that though, if you want. Sure. Yeah, I mean, we're gonna have a ton of time, it seems like, so we can we can do that after. Okay. Sure. Yeah, sure. That's something I work on directly. Yeah, so okay, so this is kind of the last part I had was this paper we're going to look at, and this is kind of how we solve actual problems with synaptic plasticity. Okay. Yeah, I'm gonna change the screen sharing to another. Okay. This is my paper, so hopefully I know it well enough to discuss it. Okay, so several questions still remain, right? Like we have these synaptic plasticity rules, but how do we get them to do anything useful, right? And we know that these neuromodulators exist, but how do we get them to solve interesting problems? And this is kind of what this recent work that I worked on does. And so it's very complicated to explain, which is kind of why I wanted to work on a whiteboard. So let me figure out how to do that. Then we can, give me a sec. Use the Google Whiteboard. Will that connect me to this machine here? Yeah, I could also do that. Okay. Okay, hi. Pin my screen if you can. Okay. Is this going well? Do you guys see me, or am I frozen here? Oh, really? I'm frozen on my screen. Okay. You guys can see me. Okay. The whiteboards are not very convenient here. Yeah. Okay. You think I could work with my laptop here? Okay, can you guys see very well? All right, so yeah, basically I have an eraser for this. Yeah. Oh, thanks. Oh, yeah, there's one right there. Okay, so let's just start by looking at the equations. Okay, we're gonna have neuron I here. And then here we have our connection. We have Wij. That's going to neuron J, right? And when we're doing any type of learning application, this is exactly what we're targeting. You know, when you do backprop, you are modifying this weight to solve some problem. And basically, the first thing we want to do is we want to separate these. And we want to get an x sub I and an x sub j. And we'll just think of these as leaking integrating fires. So when a spike travels down here, we're going to call that S sub I. And when a spike travels down here, or no, sorry. This might be a little confusing, but when a spike travels down this way, we're going to call it S sub j. Okay. Yeah, okay, they can see. And so when we get a spike happening here, we're going to model this S sub I t. This is going to be a function of time. You know, let's say we get a bunch of spikes, 1 and 0, right? Because they're binary. Basically, what this is going to look like in our trace is we're going to get a spike here, and a spike here, and a spike here, and a spike here, and then it decays back down to 0. We're going to get the exact same thing for, you know, something like this, which is going to be our S sub j of t, and this is going to be our x sub j. So it's doing something very similar to what the leaking rain fire is doing. You know, it's almost identical. Okay. And now we're going to look at STDP. There's actually a lot of ways you can model that. Now what STDP does is it's going to give us some method for updating W sub ij based on just this information. And so this was basically, I want to mention again, this was not some clever algorithm. This was just somebody said that these types of dynamics seem to be occurring in the brain. And so that's how this was derived. So the delta is going to be x sub I, s sub j. So we're going to have some learning rate, which is just some small value. Then we're gonna have x sub I, s sub j. So s sub j and x sub I. And then we're gonna have minus alpha negative x sub j s sub I. And so basically the interaction between these four variables is going to produce our weight dynamics. And what it's going to look like is synapses that this is kind of like what everyone in neuroscience says, neurons that fire together, wire together. And so this is a way of describing that. If neurons fire together, their connection strengthens and they're more likely to fire together. If they don't fire together, then their connection shrivels up and dies and goes to zero. Okay, but you know, this is not very useful for doing anything. So another thing we can do is we can introduce a new type of signal, and we'll just call this our neuromodulator. And let's think. We'll call this, so this will be 0, -1, and 1 here. And we'll call it like, I don't know, reward. And we can think back to a robot. Let's say it's just walking along and it's not getting any reward because just walking around, it's not discovering anything interesting. And the goal of the robot is to, I don't know, deliver food, right? And so let's say it delivers its food at some point t, then it gets a positive reward. So everything, all the actions that the robot did to deliver that food successfully, we want to make them more likely. And let's say it's delivering another piece of food, and during that time it smashes its head into the wall like 7 times. So we're just going to get a bunch of negative reward. And then it doesn't deliver its food at all, and we just get a massive negative reward. Something like this is not going to produce anything interesting like this. So we kind of want to combine this reward signal with this learning signal that resembles how the brain works. And so basically what people figured out is you just have to multiply them. It's that simple. So if you do some w sub ij equals, we'll call this n of t. Then we combine it with our STP rule here. And that miraculously works. Yeah. So the problem is it doesn't actually work very well. And so we kind of have to get a little bit fancier here. And what my work did that is on the screen right now is basically we figured out a way to optimize this n sub t to optimize these alphas for all of the weights so that it can solve a general set of problems. Did that make sense?
When you multiplied them, there was no negative reward. That's what happened.
When we multiply them, there's no.
I mean, it's so better than there's no negative. It's not even reward anymore.
Yeah, I mean, over enough repetitions of hitting the wall, it's gonna get that negative reward. And so if you think of how the STDP rule is defined, it was neurons that fire together, wire together. And so without the presence of a neuromodulator, basically if neurons are firing together, their behavior becomes more correlated and becomes more likely. So if you introduce this neuromodulator, which is usually 0, there's usually no learning that's occurring. But when it hits a wall, we give it that negative reward. And instead of making neurons that fire together, wire together, whatever neurons that are wired together become less likely to wire together until that behavior stops. So basically,
Does that increase like the strength of the depression side of things as far as the CPP is concerned.
What do you mean by that?
So if we get needed potentiation of depression, right?
Yeah.
That has to in terms of a CPP. So if we actually multiply that negative value within the depression with the modulator, we getting a higher negative value within the value, right?
So the modulator would be negative. Yeah, and you're saying if we have a
Yeah, if you get a
depression
there,
and we
then
multiply that.
increase that depression with the modulator value.
Yeah, then those neurons would become more likely to fire together instead of becoming less likely. So it kind of flips the sign because
Right.
those neurons not firing together produce that behavior.
Mm.
You see what I mean?
Yeah.
So we want to make basically anything that produced that behavior less likely. And then once we deliver the food successfully or do great things, then, we have this time history. And there's also another component to this called the eligibility trace, which basically accumulates these changes over a long history. Basically, you can think of it as it encapsulates all the STDP changes over a long period of time. It's just a sum of these, like another one of these types of sums, just a delta STDP with one of these coefficients.
That be driving the whole network instead of like an individual relationship between, or is it actually
So yeah, I mean,
an individual relationship?
it is still an individual relationship. I'll show you what it is. So E sub ij equals, we're just gonna copy all of this, and then we're gonna have some alpha. And then we're gonna have these weight deltas. And so what this allows us to do is it allows us to take these STDP relationships or like correlations and stretch them over a really long time period.
It's a different actor, right? Is that the same actor?
We'll call it
That's different, right?
We'll call it eta. Yeah, it's different. But it's just a filter that captures the information over a long period of time so that when we receive a reward like far in the future, we can stretch it all the way back to the behaviors that occurred during its lifetime. And I don't know if you've thought of this yet, but if we get a negative reward, there's probably a lot of behaviors that are good that are getting caught up in this negative reinforcement. Maybe it did a lot of good things, but it just happened to smash into a wall. And unfortunately, those are going to get, caught up in that negative reinforcement. But generally, over a long period of time, we're going to see that if those behaviors are not bad, they will, like on average, they'll be reinforced. So in general, we're going to see good behaviors get negatively reinforced, but on the average, it's going to be positively reinforced. And perhaps that's happened to us as people, like maybe, I don't know, you had something happen to you and you correlate that bad thing with things that had absolutely nothing to do with that. I don't know, like when I was in middle school, I used to like brush my teeth with my left hand, thinking it would give me like, I would have a better day, just like crazy middle school stuff. But you just like correlate these absolutely random things with things that aren't going to produce that outcome. And that's also what happens with rules like this, but that's also present in biological organisms. So that's kind of interesting. Okay, so basically, if we define that reward function, there's still a lot of problems. For example, what do we pick for these values of eta? Eta and alpha. And quite frankly, manually selecting these values is not going to get you what you want. And if you have this reward function, it's not going to produce sufficient behavior here. And so what you want to do is you want to create an optimizer that optimizes all of these parameters, and then you optimize them in an outer loop. And we're going to have to go into this into a lot of depth, but you optimize these parameters in an outer loop, and this is producing learning on an inner loop. Okay, so I guess the biological equivalent of that, I'm going to erase this. We'll leave that. I guess the biological equivalence, which we can think of here, is evolution, right? I mean, there's a lot more timescales between this, but this is kind of a big picture. Evolution, and then we have an individual brain, which is attached to an organism. This brain is produced by genetics, and the relationship between genetics and experience, and that's going to produce an organism. And basically, if the brain that it produces is more successful at survival, then the organism is going to produce more offsprings. And so to do this, you can actually use evolutionary algorithms, the exact same things that were presented last week. But my work uses backpropagation to optimize the learning rule, and the learning rule solves the task. So it's a little bit tricky. Okay, so one thing we talked about a lot in class was the Cinderella problem. And we had a physics environment. We had a physics environment, and we had some robot in the physics environment. But when we transfer to reality on a real robot, it doesn't really match up. If we were to use this kind of rule, it realistically wouldn't fix the problem. The underlying problem is we have a robot with a brain, and that brain needs to learn how to adapt to reality. And so kind of the process that's happening here is, let's say now we have a bunch of physics environments. So you have physics environment 1, physics environment 2, physics environment 3. We'll do 0 because we're ECE. And basically all of these have different physical parameters that are completely different. And we start off with a neural network that we want the robot to adapt to the new physics. And so we start off with a set of weights that we learned through backpropagation, which, for example, produce good behavior in a certain physical environment. And then we train the plasticity to adapt to the new physics. And so this is the outer loop problem. And this is what we train the plasticity on. So we do delta plasticity. And then we have an inner loop problem, which is all of these have an inner loop problem, which is we start out with physics we don't recognize. And then by the end of the problem, we want to have adapted to the new physics. So do you see there's like 2 optimizations happening here? Here we're updating the brain to solve the problem. Here we're updating the plasticity to be better at solving the problem. And that's what this work does. Basically, we discovered you can just apply backprop and it works really well. And all of these plasticity equations are differentiable. The only thing that's not differentiable is the spiking function. But you guys went over surrogate gradients? Yeah, so you can just use a surrogate gradient and differentiate all the way back through this time history. And you get a delta plasticity. So you're updating the etas and the alphas. And then you're learning how to learn a plasticity rule. So it's like improving the learning process itself. Yeah, and that's what that work is. And so once we've done that with all these physical environments in the simulator, this should be N. And then we take this robot, right? We get a neural network from this. We get one, a neural network. And then we get two plasticity rules. And the neural network kind of has a baseline behavior, and the plasticity rules have a type of dynamic that allows the neural network to adapt to new physics. And so when we do that, our hope is that we can just go to sim to real. Does that make sense? Yeah, so that's how you use these in a practical setting. Okay, any questions on any of that? Any questions in Zoom? Okay, well, that's all I have for today. It's pretty early. No questions in Zoom. All right, I guess yeah, thanks for coming, guys. Hopefully you learned something. Cool. All right, see you guys. Yeah, thank you guys for coming. Yeah, I need to figure out how to get the recording.
Not necessarily hardware.